So, one of my students today asked me about the sandwich theorem, or particularly the epsilon proof using a definition of convergence, the sandwich theorem. So, to start this little discussion, we will start by the usual definition, which is for an converges to some limit L if given any interval epsilon, we can find a capital N such that for every little n greater than capital N, the sequence elements an are within epsilon of L. Now that was a big mouthful, but let's draw a picture for ourselves to see if we can get this to make a little bit more sense, right? This is saying, okay, we just have some number line here, just a one-dimensional number line, and we have the an values. Let's say, I don't know, let's say this value is 0. Let's say there's a value of L somewhere, which is kind of like our target. The an values could look something like this, right? So this is a1, a2, a3, a4, and they kind of just scrunch in. So I'll do that. They kind of just scrunch in towards L, right? And this sort of is our intuitive definition of convergence. But the way that we make this rigorous is talking about epsilon. The idea here is that with epsilon, a2, a3, etc., the idea is that for any epsilon interval around this L, the idea is that if you count for large enough little n, right, that's all these ones here, after all of the little n greater than some big N are within the parentheses, little interval, right? So for this particular example, it looks like capital N is equal to 4 because the first 4 dots are outside, but the rest kind of scrunch up. And the idea is that as you choose smaller and smaller epsilon, right, arbitrarily small epsilon, if you can always find some large enough n such that the entire rest of the series is inside the parentheses, that is the idea of convergence. It's sort of saying that the infinite tail of the sequence is arbitrarily close to L. Wow, this is always a mouthful to talk about, but we can also picture this in a slightly different way. Instead of picturing it as a one-dimensional example, we can kind of picture it as two-dimensional example, where this is sort of the n value, and this is an. And now our target L is kind of it's kind of like a height almost, right? So with this way, it's a little bit easier to see because the ends are evenly spaced and goes out to infinity. 1, 2, 3. And the idea here is that they just sort of get arbitrarily close to this target, which we'll call L. Right? So you can think about it either way. And in this particular example, epsilon sort of becomes a, what do you call it? Almost like a window, right? So if this is plus epsilon and this is minus epsilon, the idea here is that an converges to L if for any given epsilon, so you could make this epsilon window as narrow as you want, the idea is that some tail of dots is going to be entirely within that window. Hopefully that makes some sense. So this leads us to our discussion of the sandwich theorem. The sandwich theorem is basically saying, let's say we're given 3 sequences, an, bn, and cn, with the relationship that an less than or equal to bn less than or equal to cn. And let's say we know that an approaches L and bn approaches L, or sorry, cn approaches L. The idea here I'm going to use the second picture because I think it's just a lot easier to see. But if this is n, this is sort of like saying there's a sequence of dots that are an, right? This is the an sequence, and there's a sequence of dots that are cn, and they both approach some limit. We'll call this limit L. And then there's a bn sort of sandwiched in between them. You could be doing all sorts of crazy things in the middle here, but it's always between them. And the idea is that the sandwich theorem tells us that it eventually converges to L as well. Okay, so on to discussion of the actual sandwich theorem, right? The sandwich theorem is sort of giving us 3 sequences, an, bn, and cn, such that, well, there's relative ordering, an smaller than or equal to bn, smaller than or equal to cn. Okay. So pictorially, I realize I've kind of drawn this backwards. This is saying that, well, if you know that cn and an converge to L, this is sort of saying that for any epsilon that you're given, you're going to be able to find an NA and an NC such that every one of the dots belonging to the C sequence after NC are within the epsilon window, and all the dots belonging to the A sequence after NA are also within the epsilon window, right? This is sort of our idea of as epsilon gets smaller and smaller, your choice of big N, capital N, might have to get larger to accommodate the idea of the dots going really, really close to the limit L. So the idea behind the sandwich problem is saying that, okay, let's say you have this AN and the CN already converging to L, and you know that BN is sort of between them. You want to show that it also converges to L. So given an epsilon greater than 0, we want to show that there exists. If you don't know what this symbol means, it's a quantifier called there exists. All right, you want to show that there exists some capital N, such that for every little n after the capital N, Bn is within epsilon of L. So pictorially, I've already drawn the epsilon and the AN and CN sequences from before. Excuse me, I think this should be I think I got myself a tiny bit mixed up because it should be C that's larger, right? Just want to keep it consistent. But the idea here is if these are the A's and they, kind of converge, and this is the C's and they also converge at some NC, ANs converge, ANs are within epsilon after NA. The idea is that, okay, let's say we've got some like wild card sequence, the BNs, right? And it goes from here to here to here to here. The question is, will this BN eventually get constrained within this epsilon window? And intuitively, yeah, it's got to be, because after it gets past, after the little n's get past NA, right, we're guaranteed that BNs are at least as large as NA, which means that after this point, they're forced to be within the window or at least as high as the floor, right? And then on the other hand, once they get past NC, they're going to be forced to be within the window from the other direction, right? They've got to be within the window within the ceiling. So this is sort of the idea here. The entire problem comes down to showing that given that AN and CN already converge to L, well, that guarantees the existence of a NA and an NC. And you need to show how this implies the existence of an, let's call it maybe like an NB, right? You need to show that there's an NB such that every little BN value after that is within the window. And you're going to need to think hard about how to relate NB to NC and NA. That's what the crux of the problem comes down to. Now, I don't want to give everything away, but I think you got to think this through and maybe play around with it a little bit. Work on your proofwriting skills. Good luck.